In a previous video, we learned about buffers and how they work. Today we're going to investigate the idea of buffer capacity, how to select a buffer for a specific purpose and dial in its pH so that it's where we want it to be, and then also look at its ability to effectively work as a buffer before it gets kind of overpowered. That's called buffer capacity. Just remember that a buffer system is an equilibrium between a weak acid and its conjugate base. So when that equilibrium is set up, when the conjugate base, A minus in this example, is present also with HA, when strong acid is added, then it'll react with the weak base and make a weak acid. And when a strong base is added, it will react with the weak acid and make a weak base. We also know that there's an important shortcut called the Henderson-Hasselbalch equation that will predict the pH, and we're going to make use of that as we explore buffer capacity. So how to make the buffer that you want? The first thing you want to do is pick an acid-base conjugate pair. So if you want a buffer that's got a pH of less than 7, you're going to want to choose an acid that has a pKa that's close to the target pH. Why do you want to do that? Because if the ratio of A minus to HA is 1, then the pH and the pKa would be exactly the same. Now, messing with this ratio of A minus to HA concentration, or moles, allows us to adjust a little bit up or down from pKa, but if you're not close to pH with your pKa, then that'll be very hard to do. If you want a buffer that's at pH greater than 7, choose a base that has a pKb that's close to your target pOH, and then combine that with its conjugate acid. So here's an example. If you wanted to have a buffer at pH 4.85, which of the following pairs would be the best choice? Well, this would be a poor choice because pKa is going to be around 10. Just looking at that number there, pKa is going to be approximately 10. And this one, pKa is going to be approximately 4, maybe a little bit less than 4. So that's probably not a good choice. But these two are going to have pKa's that are around 5, somewhere in the right zone. So either of those might be a good choice. If we actually calculate this pKa, it's 4.74. If we actually calculate this pKa, it's 4.89. So either of those would be an okay choice for this buffer. The next thing you want to work on is making the minor adjustment. You're going to tweak the ratio of HA and A minus to dial in just the pH that you want. So if, for example, say you wanted a buffer at pH 4.85, that's the example that we're using in the previous slide, and we're going to use acetic acid, which remember has a pKa of 4.74, with its conjugate base, which would come from sodium acetate. The question is, how many grams of sodium acetate should you add to 1 liter of a 0.1 molar acetic acid solution? Let's go to a space that has more room to work and solve this problem. Remember that pH is equal to pKa plus the base 10 logarithm of the number of moles of conjugate base, which in this case is the acetate ion, divided by the number of moles of HA, which is in this case acetic acid. Now we know everything in the Henderson-Hasselbalch equation except for that. We know the pH, the target pH, that's 4.85. We know pKa is 4.74. And we know that the number of moles of HA here, acetic acid, is 1 liter at 0.10 moles per liter. That's 0.10 moles. Let's take 4.85 and subtract 4.74. That's going to be equal to the log of the number of moles of acetate ion over 0.10 moles. If we take 10 to both sides, it's 10 to the 4.85 minus 4.74. That's equal to just number of moles of acetate ion over 0.10 moles. 10 to the 4.85 minus 4.74 is 1.29. So that's the number of moles of acetate over 0.10 moles. Solve for the number of moles of acetate ion, and you get 0.129 moles. So we want 0.129 moles of acetate ion. Every sodium acetate is going to give us 1 mole of acetate ion. So we also want 0.129 moles of sodium acetate. Sodium acetate is 82.034 grams per mole. We wanted grams, so we have to do this step. And this works out to 10.6 grams of sodium acetate. That's how much we'd have to put in that liter of 0.1 molar acetic acid to get the buffer with the pH that we want. So once you pick out an acid-base pair, and then you tweak the ratio to dial in the pH, the next thing that you have to do, and this is a little bit more complicated, is to find out what concentrations are you going to have for the required capacity for this buffer. So say you want to buffer at pH 4.85 using acetic acid and sodium acetate. It's the same buffer that we've created before. What concentration of acetic acid and what mass of sodium acetate keeps the pH from changing more than 0.5 pH units if 0.01 moles of strong acid or strong base is added to a liter of the buffer? Now, what we saw from the work that we did previously is that to dial in the pH to 4.85, we have to have the moles of acetate ion be greater than the moles of acetic acid. It was 0.129 versus 0.10 moles of acid. So that means this is going to be better at buffering acid than it is at buffering base. So let's do our calculations contingent on its ability to buffer base, not acid. Let's go to a workspace where we have some room to spread this out and figure this out. Let's look at what happens when our strong base is added to the solution. OH minus is going to react with HA, the acetic acid, and it's going to form H2O and some acetate ion. Let's make a BCA chart. Before, we have added 0.01 moles of strong base. That's the capacity that we want. We have some number of moles of HA here. We kind of want to figure that out. Don't worry about water. And we have some number of moles of A minus. What's the change? Well, we're going to buffer all of that strong base that was added. So that afterwards, none of this is left. We have the starting number of moles of acid minus 0.01, and we have the starting number of moles of conjugate base plus 0.01. Okay, going back to the Henderson-Hasselbalch equation, we want to make sure that the pH doesn't rise more than 0.5 pH points from the target pH. The target pH is 4.85. 4.85 plus 0.5 is 5.35. That's going to be equal to pKa, remember that's 4.74 for this acid, plus the base 10 logarithm of base moles, which is whatever was the starting number of moles, plus 0.01 moles, over the starting number of moles of acetic acid, minus 0.01 moles. So that's base moles over acid moles, the way the Henderson-Hasselbalch equation is written. If we take 5.35 minus 4.74, that's 0.61. So 10 to the 0.61 is equal to number of moles of base plus 0.01 over number of moles of acid minus 0.01. 10 to the 0.61 is 4.07. So that's equal to number of moles of base plus 0.01 over number of moles of acid minus 0.01. So, doing a little algebra, 4.07 times number of moles of acid minus 0.01 equals number of moles of base plus 0.01. But remember, we had figured out in the previous setup for this that the number of moles of base is 1.29 times the number of moles of acid. So that means 4.07 times the number of moles of acid minus 0.01 equals 1.29 times the number of moles of acid plus 0.01. Then this just becomes an algebra problem, which you can solve, which comes out to the number of moles of acid here is equal to 0.018 moles. So that means the number of moles of base is going to be 1.29 times that amount, which comes out to 0.023 moles. So if we take 0.023 moles of sodium acetate multiplied by sodium acetate's molar mass, which was 82.034 grams per mole, this comes out to 1.9 grams of sodium acetate that we would have to add. And all of the acetic acid came from 1 liter, and we needed 0.018 moles, so that means the concentration of acetic acid here would have to be 0.018 molar. Let's do one more example problem here. Figure out how to use one of these acids and their sodium salts to make 500 liters of a buffer that'll keep a pH between 4.2 and 4.4 if 0.02 moles of HCl or NaOH, that's our strong acid, strong base, are added. Okay, so our target pH is 4.30, halfway between here. So we want a pKa that's close to that. This would be a bad choice. That would probably be a bad choice. Let's look in more detail here. pKa for this acid is 4.89. That would be okay. pKa for this acid is 4.19. That's probably our best bet, is to use benzoic acid and sodium benzoate. Okay, so we want to have a target pH of 4.30. 4.19 is our pH. This is just the Henderson-Hasselbalch equation, plus the base 10 logarithm of number of moles of base over number of moles of acid. So 10 to the 4.30 minus 4.19 is going to be the number of moles of base over the number of moles of acid. Do a little bit more algebra. 1.29 is the number of moles of base divided by the number of moles of acid. And that means the number of moles of base is 1.29 times the number of moles of acid. That turned out to be just the same as the previous problem. It's just a coincidence. It's not something you can rely on. Okay, we have more base than acid, so this is going to be better at reacting to acid than base. So again, we're going to base our calculations off how well it buffers base, strong base. So OH minus plus AHA is going to make water and A minus. BCA chart. This is for if 0.02 moles of strong base is added, 0.02. This will be the number of moles of HA originally, and this is the number of moles of A minus originally. Change, we're going to buffer all 0.02 moles. Afterwards, this will be the starting moles of HA minus 0.02, and this will be the starting moles of A minus plus 0.02. So back to the Henderson-Hasselbalch equation. The highest we want our pH to get is 4.40. Starting from a pKa of 4.19 plus the base 10 logarithm of original moles of base plus 0.02 divided by the original moles of acid minus 0.02. So we can take 4.4 minus 4.19 and raise 10 to it. So we get 10 to the 0.21 is equal to number of moles of base plus 0.02 over number of moles of acid minus 0.02. 10 to the minus 0.21 is 1.62, and that's equal to number of moles of base plus 0.02 over number of moles of acid minus 0.02. So 1.62 is 1.29 times the number of moles of acid plus 0.02 over the number of moles of acid minus 0.02. Do some algebra here, and we find out that the number of moles of acid is 0.16. So let's move up here. That means the concentration of our benzoic acid is 0.16 moles in a half a liter, which comes out to 0.32 molar. So we're going to start out with 500 milliliters of 0.32 molar HA. How much base are we going to add? Well, 1.29 times 0.16 moles is how much sodium benzoate is going to be needed, and that works out to 0.21 moles. So we'll take 0.21 moles and we'll multiply it by the molar mass of sodium benzoate. Now, sodium benzoate is going to be NaC6H5COO. So working out that molar mass, it comes out to 144.105 grams per mole, and that's 30 grams of this. So we'll take 30 grams of sodium benzoate, put it in 500 milliliters of 0.32 molar benzoic acid, and we'll have the buffer that has the pH that we want and the capacity that we want.